Hello?
Hello, can you hear me?
Yeah, I can hear you. You can hear me?
Your voice is a little bit low.
Okay, one second. Hello, hello.
Yeah.
Can you hear me right now?
Wait, I try not to use my earpiece. Wait.
Yeah, yeah. Just check every setting, like make sure that you can hear me. Anyway, I'll record the class, so you will be able to watch the video later. So,
Um, okay, yeah. Now it's better.
okay, okay. So, you are preparing for the Maths Olympiad in Singapore in June, right?
Yes.
Okay. And number theory is what you want to start off with.
Yeah.
Okay. So, uh, we'll begin from the basics, and once we cover number theory, then we'll move on to other topics like geometry and combinatorics and
Okay.
algebra and all. So we'll start off with number theory right now, and uh, I will discuss some theory and we'll do some problems. Okay.
So,
And
may I ask several questions before we start?
yeah, yeah, tell me.
First thing is that do you use WhatsApp or some other apps like that?
Yeah, yeah. WhatsApp, you can contact me on WhatsApp. I'll send my number. So this is my number. This is country code, and
Wait, I add no.
yeah, yeah.
Uh,
91 is a country code, and 900-452-3817.
uh,
You can message me and I'll see. Yeah,
I message you no.
yeah, yeah, I got it. One second. By the way, how is your name pronounced? How do you call you? What do you call yourself?
It's a Houser. It's a
Hausa.
Yeah, it's a Chinese name.
Okay. So you are also Chinese,
Yeah.
but you stay in Singapore.
Yeah.
Your parents work in Singapore.
No.
Okay.
I mean, like, also the majority of Singaporeans are Chinese. Also, I mean,
Yeah,
it's
yeah.
a kind of. Mm. Also, another thing is that
Huh.
could you not upload our lessons to YouTube?
No, no, these will not be uploaded to YouTube. I will only record it and share it with you.
Okay. Thank you.
Yeah, yeah.
Okay. Okay.
So
I have no
because
questions.
if it is a personal class, then it will not be on YouTube.
Okay.
What else? Any other questions? Anything?
No.
Okay. Fine. So we'll start off with divisibility. So that is one of the fundamental concepts in number theory, and that is the basic thing that we have to begin with. So obviously you know what divisibility means, right?
I mean, just like uh, two can divide
Yeah,
six.
yeah, yeah. Yeah. So an integer which is not equal to 0 divides b if b can be written as a into c, where c is another integer, right?
Yeah.
So b is going to be called multiple multiple of a, and a is going to be called factor of b, right? And we write this as we generally write this as a divides b. This is the symbol. This is the symbol for a divides b. So basically a is something 2 divides 6, the example that you gave, right? Now if something does not divide something, we write it like this: a does not divide b. This is does not divide. Are you able to understand the handwriting and all?
Yeah.
Okay, fine. Uh, so then some basic properties of divisibility that you should be clear on. So for example, if A divides B and B divides C, that implies that A divides C. Is this clear? Like,
Yeah.
because A divides B means B is equal to A into K1, and B divides C means C is equal to B into K2, where K1 and K2 are two arbitrary integers, right?
Yeah.
Therefore, now C is equal to B into K1, B into K2, and B you can replace. So you can say A into K1 into K2, right? So
Yeah.
you have A into K1, K2. So this makes C is equal to A into K1, K2. So therefore, A divides C, right? In a similar way, you can prove things like this. If A divides B and A divides C, then A divides B plus or minus C, right? Tell me if it is too fast or if you need to slow down or whatever, right? So,
I think this is okay.
yeah, so this is clear, right? This is obvious.
Yeah.
Similarly, you can say that A divides B and A divides C, then A will obviously divide any combination of B and C, like L times B plus M times C, where L and M are integers, right? Any combination of B and C, correct?
Yeah.
Then, if A divides B and B divides A, then what can we say about A and B?
They are the same.
Yeah, then they are equal to each other or plus or minus of each other, right? Correct.
Yeah.
So divides B and B divides A implies that A and B are plus or minus of each other. So now, using these basic properties, what we want to do is prove certain theorems. So for example, if can you prove that x plus y divides x power 2n plus 1 plus y power 2n plus 1, where n is a natural number? N is a natural number. This is, for example, a question say. You have to prove this.
Should I use the uh
You can
remainder
use
theorem?
factor theorem or remainder theorem, right?
Yeah.
You can say that this is a polynomial, and if I have to say that x plus y is a factor, then instead of x you can put minus y in this, right? Correct. You can check the value of p of minus y, right?
Yeah.
And when you do that, you'll get minus y power 2n plus 1 plus y power 2n plus 1, and therefore that will become 0. So that means that x plus y is a factor, right?
Yeah.
You can do it like this, but you should also know the actual factorization of this. Like if you just do long division, like you must have known division of polynomials, the method to do that, right?
Yeah.
So if you just divide, say, this polynomial by this polynomial, you'll probably first start off with x power 2n, and then you'll get x power 2n plus 1 plus y into x power 2n, and then you'll subtract, right?
Yeah.
And slowly you will have to write many terms here. So if you do long division, you will realize that x plus y multiplied by x power 2n minus x power 2n minus 1 y plus x power 2n minus 2 y square minus so on, and goes on till plus y power 2n. This product is equal to x power 2n plus 1 plus y power 2n plus 1. You can check this by putting some small values of n. So, for example, if you put n is equal to 1, this is basically x cube plus y cube, right? And x cube plus y cube can be factorized as x plus y multiplied by x square minus xy plus y square. Correct?
Yeah.
That is an example of this general factorization. And this general factorization can be obtained by just dividing. You divide the x power 2n plus 1 plus y power 2n plus 1 by x plus y, and you'll get this. The reason we are discussing this is there might be questions where you need to know that if you have x and y in odd powers and they are summed, then they will be divisible by x plus y. The easier way to think about this is through factor theorem, right?
Yeah.
Okay, let's solve a question. Let's see whether we are able to do it or not. This is the question is this: the equation x square plus px plus q is equal to 0 has rational roots. Has rational roots where p and q are integers. Prove that the roots are integers. Prove that the roots are integers. So one thing that I have a question for you is the exam that you're preparing for is a subjective type exam, right?
Yeah.
The
Trust
second
me.
level that you're preparing for,
Uh, the open section.
the open section, it's you have to show your work, right?
No. I for the first round, I think I just need to submit the answer.
Okay, okay. But there, I thought I saw one or two papers there where there is a open section has one level which is having multiple choices or something, and one level which is not multiple choice, but you have to do some work and all, right?
Yeah, there are two rounds.
Okay, okay. Fine. So anyway, what I'm saying is you will have to work on proof style of questions, right? Like it's not like you can ignore that because ultimately open section and higher levels you'll have to worry about how to write a proof and all.
Yeah.
Correct. So don't prepare specifically for the exam. Prepare in general so that your maths is better. Like you should not be like just because there are no proof questions in your open section exam, I will not do it. Right?
Yeah.
Okay. So this question, let's look at it. Uh, the equation has rational roots. P and Q are integers. You have to prove that the roots are also integers. You obviously know the quadratic formula, right?
Yeah.
Yeah. So basically, you can say the roots of this are x is equal to what?
Uh, minus b plus minus
Hmm.
square root of b square minus 4ac over
Hmm.
2a.
So in this case, it will be p square
Yeah.
minus 4q
Yeah.
by 2, right?
Yeah.
Okay. So these are the two roots here. What are we given? We are told that the roots are rational, right?
Yeah.
So p and q are integers and the roots are rational. Like obviously, if the roots are rational, then the square root part has to come out as a rational thing, right? You cannot have a square root which is not a perfect square, right?
Yeah.
Otherwise, if it is not a perfect square, then there is an irrational thing that is left, right?
Yeah.
So if the roots are supposed to be rational, the p square minus 4q part must be a perfect square, right?
Yeah.
Okay. So from here, think about what that means and how you can approach this further. P square minus 4q is a perfect square we are getting. So take
Like,
cases.
So
Uh,
should I let it be some n square and
mhm.
then I rearrange?
So you can try that. That is one way to try it. Or, but think about one thing here. Eventually, if the roots are supposed to be integers, or you have to prove that the roots are integers, then the part that comes on top must be divisible by 2, right?
Yeah,
Like it has to be even. The top part has to be even somehow,
yeah,
right? So you have to basically prove that minus p plus minus this thing is even, right?
yeah.
So that is the thought that you should focus on. Like you think about that. Like how would you prove that that is even? You already know that p square minus 4q is a perfect square, and you have to prove that this part is even.
Oh,
So here is where you should think of two cases. Case one, where you say that p is even, and case two, where p is odd, right?
uh-huh.
Correct.
Yeah,
Because there is no other possibility. P is an integer, so must be even or must be odd. So if p is even, what happens? Look at p square minus 4q.
it's even.
P square is also even, and 4q is also even, right?
Uh, yeah, so it comes out to be even.
Even, right? And p square minus 4q is an even integer, and it is a perfect square also, right?
Yeah,
So then root of p square minus 4q, like think of a perfect square which is even, right?
yeah,
So if you think of perfect square which is even, it must have powers of 2, but it cannot have a power of 2 which is not a multiple power of 2, right?
yeah,
Like it cannot have just 2 into something odd, right?
yeah. So it's like
Yeah.
have four something.
Yeah, it has to have 4 or something, because otherwise it will not be a perfect square, right?
Yeah,
So that means that if p square minus 4q is even, then root of p square minus 4q will also be even, because one power of 2 will come out, right?
yeah,
Is also even. And if that is even, then minus p, which is even, plus minus something even, will remain even, right?
yeah,
So in the case that p is even, you can prove that the top numerator is even, and therefore the x value or the root is going to be an integer,
yeah.
right? Okay. So now let's think about the case when it is odd.
Oh, so p square is odd
Hmm.
and p square minus 4q is odd, and the
Correct.
square root of it is also odd,
Hmm.
and the minus p plus or minus an odd number is
Correct.
an even number.
So it is an even, is an odd plus minus an odd. So odd plus minus odd becomes even, right?
Yeah,
So divided by 2, it is going to be an integer, correct?
yeah,
So basically, we are getting it by thinking about odd even cases for p. And we also had one more point to realize that p square minus 4q must be a perfect square, right?
yeah.
This is one way to do it. As we go ahead, we will do something called rational roots theorem in algebra. You might have heard of it, maybe you have not heard of it, but later we'll study this, and that gives you the answer immediately here. But later we'll study this. Right now, just we'll just focus on number theory portions for this.
Okay.
So let's look at another question. This is this. So find the number of positive integers n, positive integers n, for which first n is less than equal to 1991, second 6 is a factor of n square plus 3n plus 2. So basically, you have to find how many positive integers are there such that it is less than 1991, and 6 is a factor of this. Correct?
Yeah.
So let's think about this.
So like n square plus 3n plus 2 is
Mm,
n plus 1
mm,
times n plus 2.
correct.
Then I just discuss the, how do I call it?
6 divides basically n plus 1 and n plus 2, right?
Then n plus 1 and n plus 2 must one of them is odd and one of them is even.
Correct. Odd and even. Either, or it could be even or odd. So basically you can say that one of them is even, therefore 2 divides one of them, right?
Yeah.
Correct.
So
So
just to say 3 divides either n plus 1 or n plus 2.
correct, correct. So from here, actually, you can say that if 6 divides this, then 2 divides, obviously 2 should divide this, and also 3 should divide this, right?
Yeah.
Correct. Okay, great. This condition, for example, tells you something about n.
So like n is either congruent to 1 or 2 mod 3.
Correct. So n cannot be a multiple of 3, right?
Yeah.
Only then will 3 divide n plus 1 or n plus 2, right?
Yeah.
Correct. So n cannot be multiple of 3. So obviously you can eliminate all the numbers like this 3, 6, 9, and so on till 1989, right?
Yeah.
Those are not possible, right?
Yeah.
Uh, this, however, doesn't tell us any this doesn't give us any restriction, right?
Yeah.
Because 2 will always divide two consecutive integers,
Yeah.
right? So the only restriction that you are getting are n cannot be these, right?
Yeah.
So now you just count how many numbers are there less than equal to 1991, right?
Yeah.
1, 2, and then exclude 3, 6, and all, right?
Yeah.
So basically, it will be 1991 minus basically number of multiples of 3, right? Correct. Till
Yeah.
1991. So you'll do a division by 3 and take the greatest integer less than equal to 3, less than equal to this.
Yeah.
Later we'll discuss all of this, but I think you are already aware of these terms, right?
Oh yeah, it is
Yeah,
the largest integer not exceeding.
correct,
Eh,
correct. Yeah, yeah. So you'll get this, and the answer will be this 1328 will be your answer here. So, okay, so we are able to do some of these basic questions. Let's do another slightly tricky one. Uh, this is this one. Show that 1 power 1997 plus 2 power 1997 plus so on till 1996 power 1997 is divisible by 1997. We have to prove this.
So it's like 1996 is minus 1,
Mhm.
and then 1995 is minus 2.
You are saying,
The congruent.
huh, you are saying congruency.
Yeah.
You can also group it in a way, right? You said look at the first one and the last one,
Yeah.
and the second last one, for example, second last one was this, and second one from the beginning is this, right?
Yeah.
You can group these, and we know the property. If you recall the property x plus y will divide x power odd plus y power odd, right?
Yeah.
So now look at this. First and last, if you group together, then 1 plus 1996 should divide this, right?
Yeah.
1996, 1997 divides 1 power 1997 plus 1996 power 1997. And similarly, 1997 will divide 2 power 1997 plus 1995 power 1997, right?
Yeah.
By this property that we saw earlier,
Hmm.
correct?
Yeah.
And notice that there are even number of terms here. So you will always be able to make groups of two, right?
Yeah.
There's nothing that is going to be left behind and all, right?
Yeah.
So the whole thing will be a collection of statements like this. And you can say that since all of these are divisible by 1997, the expression entirely is also divisible by 1997, right?
Yeah.
Okay. So next we look at the division lemma by Euclid. Euclid's division lemma. It says, like, you probably know what it says, right?
Eh, I I'm not sure.
Okay. Okay. So if a and b are any two integers, where a is not equal to 0, then there exist unique integers, q and r, such that b can be written as a times q plus r.
Oh, yeah, I know this.
Yeah, and r is less than mod of a. This is obvious, right? This is division basically, right?
Yeah.
If a and b are any two integers and a is not 0, then we can say that there are unique integers q and r. Q is the quotient, r is the remainder, right?
Yeah.
Such that b can be written as a times q plus r, right?
Yeah.
Where r must be less than the magnitude of a, because otherwise you would have taken one more a here, right, and made it q plus 1,
Yeah.
right?
Yeah.
So one thing to realize here is that it is supposed to be a unique integer. What does unique word here mean? It means that there is only one way to write this in this way, right?
Yeah.
Like there is no alternate way to express b divided by a. You get only one particular q and r, not some multiple answers, right?
Yeah.
Correct. So this is your division lemma, and sounds very straightforward and very simple, but you will see that applications of this will be interesting. Okay.
Okay.
So we'll look at one more question here. So we have to prove that for any natural number n, for any natural number n, this expression e is equal to 2903 power n minus 803 power n minus 464 power n plus 261 power n. This expression is divisible by 1897. We have to prove this.
Okay.
Anytime you have such a weird question, you should think about the number by which we have to prove divisibility. So maybe just do a prime factorization of 1897 first. It is divisible by what prime factor?
7
Yeah, 7 into 271,
is
right?
71 divisible.
271 is also a prime number.
Okay.
You will realize that by checking all the primes less than what number?
The square root of it.
Correct. So 17 square is 289. So you should check primes till 17, right?
Yeah.
Or till basically 13 or 17, you can check. You'll realize that none of them will divide 271, right?
Yeah.
Okay, so if I have to prove that a big expression is divisible by 1897, I need to prove that the expression is divisible by 7 also and 271 also, right?
Oh yeah.
Correct. So think of those things and now try it. Basically prove that 7 divides E and 271 divides E. 'Think about this property. X minus y will always divide x power n minus y power n, right?
Yeah.
This property should be useful for thinking about this expression.
Oh, yeah. So it's like 2903
Hmm.
uh, uh is
Power n.
it is congruent to 2 not to 5. It's congruent to 5.
Mhm.
Then 803 is also congruent to 5. So like it's basically 5 to the power n minus 5 to the power n.
Correct. Basically, what you're saying is this minus this will be divisible by 2903 minus 803, right?
Yeah.
If you subtract this, you'll realize that this is basically 2100, right?
Yeah.
2100 divides this, and from here, you can say that it is minus 464 power n minus 261 power n, right?
Yeah.
So you will again say 203 divides this, right?
Yeah.
The difference between these, right?
Yeah.
By using this property.
Yeah.
Now you will see that 200 is divisible by 7, and this is obviously divisible by 7, right?
Yeah.
So 7 divides this also, and 7 divides this also, right?
Yeah.
So you have 7 divides the whole thing, correct?
Yeah.
Now, for the other thing, you just have to take a different grouping. Like if I do 2903 and 464 together and 803 and 261 together, right?
Yeah.
Then you will realize that 2903 minus 464 will be 2439, will divide 2903 power n minus 464 power n, right?
Yeah.
And the other thing will give you 803 minus 261, which will be 542, will divide 803 power n minus 261 power n, right?
Yeah.
And you will realize that 542 is 271 into 2, and this will be 271 into 9, I think. Because if you add 271 to it, it is becoming 2710, right?
Yeah.
So both of these are divisible by 271, correct?
Yeah.
So again, a combination of two expressions which are divisible by 271 will give us the overall E expression, which is divisible by 271, right?
Yeah.
See, the reason why I'm not using congruency right now is because we have not discussed congruency. So there will be a time when we do congruency and we'll discuss questions using the congruent principle. But right now, we don't need it. We will solve it by basic stuff like this, right?
Yeah.
Are you getting what I'm saying?
Yeah.
Okay. Uh, the next thing is GCD, greatest common divisor. So what is greatest common divisor?
Like the greatest integer that divide
So
both two numbers.
correct. So A and B, if you have two numbers, this expression stands for GCD of A and B. And the way to get GCD is one way is simple. Write A as 2 power P1, 3 power P2, 5 power P3, and so on, right?
Yeah.
And write B also as 2 power Q1, 3 power Q2, 5 power Q3, and so on. Correct?
Yeah.
Once you have both of these prime factorizations, what do? You take whichever prime factors are common, right?
Yeah.
And take the highest common power, right?
Yeah.
So if suppose P1 was 4 and Q1 was 3, right?
Then pick three.
Then you'll pick 3 and so on. If you have any common prime factors, you take the highest powers and therefore from there you can construct your GCD number, right?
Yeah.
So that is the standard method that everyone learns. Also, there is another method
Or
of finding GCD.
is it the Euclidean
Hmm.
algorithm?
Yeah, the Euclidean algorithm. That is another method. So what do you know about this? How do you get GCD from this?
I almost forgot.
Okay. So the method is simple. Uh, it's basically saying that GCD of A and B will be equal to GCD of A and A minus B. Okay. This is the basic idea. Excuse me. So think about it. Let's pick two numbers and see if this is true or not, right? Let's pick any two numbers. Let's say 14 and 21, right?
It's seven.
We know the answer, but we are just checking whether this thing works or not, right? So we are saying, okay, A and B are 14 and 27. Then we'll say GCD of A and B. Let's call this one as A and this one as B, the larger number as A, right?
Yeah.
Should be equal to GCD of A and A minus B, which is equal to 7, right?
Yeah.
Correct. And now you can see that one of the numbers is a multiple of the other. So the lower number is the GCD, right?
Yeah.
As soon as you get to a stage where one of the numbers is a multiple of the other, then obviously the lower number is the GCD, right?
Yeah.
So we are getting 7 by this method, where in this method we are reducing it to a situation which is obvious. This is obvious what is the GCD here, right?
Yeah.
Now let's take a bigger number, for example, GCD of 143 and 275, let's say, right? I have just made up the numbers.
Okay.
Okay. So I will apply the Euclidean algorithm. I'll say is equal to GCD of 275 and the difference between them, right? Difference between them is 132, right?
Yeah.
Okay, now I think we'll get stuck here because after that, okay, I have made a mistake. Okay, one second. I have made a mistake because what I said was GCD of A and B was equal to GCD of, I said A and A minus B. I should have said B and A minus B because then you are getting to a smaller level, right?
Yeah.
Like if I keep A there, then what will happen? Then you have subtracted and kept the bigger number. Then again, next step you will come back to the original thing, right?
Yeah.
You understand the problem? Like you need to come down.
Oh, yeah.
right? So now let's go back to a question. So 275 and 143 is what I said. So I will say it is equal to GCD of 143 and 132, right?
Yeah.
And now I'll keep the smaller number and the difference. 132 and this is 11, right?
Yeah.
And
So it's a multiple of 11.
correct. It is directly a multiple of 11. However, now there is a way to bring it down slowly. Answer is 11, you can guess. Answer is 11, but the algorithm now is correctly written, so you can bring it down now. See, you can write smaller number and difference, right? So it will be 121
Yeah.
and 11, right?
Yeah.
And then it will be 110 and 11, right?
Yeah.
And slowly in step by step manner, you can get to GCD of 11 and 11, right?
Yeah. Which is
Is
11.
11, right? So this is the method by which you are doing what? You're doing repeated subtractions, right?
Yeah.
Repeated subtraction. Every time you're subtracting the smaller number from the bigger number, right?
Yeah.
And the difference is kept there and the smaller number is kept there, right?
Yeah.
So this repeated subtraction can be reduced to a division, and you can just say that instead of repeatedly subtracting, I will just divide, and I will reduce the number of steps required to do this algorithm, right? And what the Euclidean division algorithm method of finding GCD says is this: GCD of A and B will be equal to, so if you write B as AQ plus R, right? Then
Yeah.
GCD of A and B will be equal to GCD of A and R. This is the thing.
Why is it so?
Why is this so? Because think about it. Uh, if you do GCD of A and B, then what do you do? Next step, would you would have done? Let's say A was the bigger. Here B is the bigger number, right?
Yeah.
B is the bigger number, so it will be B minus A comma A, right?
Okay.
Because I would have done subtraction and smaller number, right?
Yeah.
Correct. And then what would you have done? Then you would have done GCD of maybe B minus 2A comma A. Depends on how big A and B are, right?
Well, like, why the formula above is true? I mean, like, why GCD A comma B equals GCD B minus A comma A?
Correct. Okay. So we can discuss that. So if you have something like this, GCD of A and B is equal to GCD of A comma B minus A. Why is this true? Because let D be the GCD of A and B, right?
Yeah.
Correct. Then obviously we know that A can be written as K1 times D, right?
Yeah.
And B can be written as K2 times D. K1 and K2 are some integers, right?
Yeah.
And obviously D divides both of them, correct?
Yeah.
Now let's try to figure out what is the GCD of A and B minus A, right? So
Yeah.
now A is K1D, and what is B minus A,
Or K2 minus K1D.
right? So this is K2 minus K1 multiplied by D, right?
Yeah.
Now, if you think about it, if D was the GCD, then K1 and K2 have no common factors, right?
Yeah.
Have no common factors, because otherwise they would have taken one factor out from there also, no, if they had common factors, right?
Yeah.
So if K1 and K2 are co-prime to each other, then obviously if I take GCD of these two numbers, K1 and K2 minus K1 are also having no common factors, right?
Oh, yeah.
Right.
Yeah.
So when you take GCD of A and B minus A, still you will get D only, right?
Oh, yeah.
Right.
Yeah.
So that is why this works. Okay. And in a similar way, you can prove that also if B is equal to AQ plus R, right?
Yeah.
and R is less than mod A and stuff, right?
Mm-hmm.
This is the division algorithm. Then you can prove that GCD of B and A is equal to GCD of A and R. Again, in the same way, how? Assume D to be the GCD of B and A, right?
Yeah.
Then you can write B as D times K1 and A as D times K2, right?
Yeah.
And K1 and K2 are co-prime, right?
Yeah.
And then use the division algorithm and find out Q and R in terms of this and check the GCD of A and R, right?
Oh, yeah.
So you can try that yourself, but you will get it. Okay. So
Okay.
now what we will do is we will look at a random example and see how this division algorithm works, how you get GCD practically in a situation. So let's say we have to find GCD of 72 and 245, 44, let's say, right?
Yeah.
So what we know is 244 can be written as 72 multiplied by 3 plus that will be 216 plus 28, right?
Yeah.
Correct. So now because we have to find GCD of A and B, my B is this and A is this, it will be equal to GCD of 72 comma 28, right?
Yeah.
Because A is this and R is this, right?
Yeah.
So once this is equal to this, then again I repeat the same process. And I'll say I will divide 72 by 28 and I will say 28 remains and whatever is the remainder comes. 28 2s are 56 and then 16, right?
Yeah.
Correct. And then again, same thing. I will divide 28 by 16. So 16 remains and whatever remainder, so 12, right?
Oh,
And then it will be GCD of divide 12. So 12 remains and 4. And now this answer is 4, right?
yeah.
So this has been done in how many steps? Like 3, 4 steps, right? Like
Yeah.
3, 4 steps, correct?
Yeah.
If you understand this process, you understood this part, right?
Yeah. I think so.
Okay. So what you should do is try to figure out why this is true, just like we did for the subtraction method, right?
Yeah.
Try it yourself. If you don't get it, then we'll discuss it in the next class. Okay.
Okay. Okay.
Try it yourself. Try to see why this is true, a proof. And right now we got the GCD as 4 by this division method. Let's also check by the subtraction method if we get it or not. 72 and 244, let's say. So it would have been GCD of 72 and the difference between them, right?
Yeah.
So 44, 244 minus 72 will
One
be
172.
172, right? Correct. And then it will be GCD of lower number and difference between them, so 100. And then it will be GCD of lower number and difference between them, which is 28, 28 comma 72, right?
Yeah.
And then it will be GCD of lower number and difference between them, which will be 30, 44, right?
Yeah.
And that will be GCD of 28 comma 16. And now see, it is coming, the same thing has come, right? 28, 16.
Yeah.
So notice that we will get to the same thing, but we will get to it in a slightly longer number of steps, right?
Yeah.
Basically, the GCD Euclidean method of finding GCD is doing either repeated subtraction you can do, or you can do the division method, right?
Yeah.
Both will eventually give you the answer, correct?
Yeah.
Okay. Now, a few properties that are important. So first of all, the symbol for GCD is A comma B. And obviously GCD of any two numbers is always greater than equal to 1, right?
Yeah.
If if A comma B GCD is 1, then A and B are said to be coprime, are said to be coprime to each other, or they have no common factors, right?
Yeah.
Then we can say that GCD of A and B will be equal to GCD of A plus some K times B comma B. Now, this is what the property that we just now proved, right?
Yeah.
Because if k is -1, then you get a minus b comma b, right?
Yeah.
So basically, if you have GCD of two numbers a and b, then any linear combination of a and b comma b will have the same GCD, right?
Yeah.
Correct.
Yeah.
Now the next property is, if GCD of a and b is equal to g and d is a common divisor, of a and b, then d
DD.
divides g, right?
Yeah.
Because g is the greatest common divisor and d is another common divisor, right?
Yeah.
So the normal divisor will be dividing the greatest common divisor, right?
Yeah.
This is obvious if you think of the prime factorization of a and b, right?
Yeah.
Correct. Okay. Then another property is this: if a and b's GCD is equal to g, then what is the GCD of a by g and b by g?
Oh, is it one?
1, right? So if you
Yeah.
remove the greatest common divisor from both the numbers, then obviously they will become co-prime, right?
Yeah.
Correct. Uh, then another a very important property, this one, uh, if GCD of A and B is equal to G, then there exist two integers x and y such that G can be written as x times A plus y times B. So think about this for a moment. Basically, he's saying that if the greatest common divisor of two integers a and b is g, then you can express that g in terms of the a and b by using some two other integers. You understand?
Yeah. I mean,
So,
is it a,
so there is a proof for it, okay? And you can there is a way to get those x and y. So think about it. Like, let's see. We have, let's say, GCD of two numbers. Let's take two numbers, for example, 48 and uh, 84, right?
yeah.
Okay. And we find the GCD first. So let's find it by the division method. So I will say GCD 48, comma, whatever is the remainder. So when I divide, it will be 36, right?
Yeah.
And then lower number and whatever is the remainder. So 36, comma 12, right?
So it's 12.
So 12 is the GCD, right?
Yeah.
Correct. Now, the question is saying that I should be able to write 12 in terms of x times 48 plus y times 84, right?
Yeah.
So let's see how we will do that. Uh, so what I will do is this series of steps that I did here, I will write it like this: 84 is equal to 48 multiplied by 1 plus 36, right?
Yeah.
This step, and then I can say 48 is equal to 36 multiplied by 1 plus 12, right? And
Yeah.
finally 36 is equal to 12 multiplied by 3 plus 0, right?
Yeah.
Okay, so now see, from this step you can write 12 as 48 minus 36, right?
Yeah.
Correct.
Yeah.
And from this step you can write 36 as 84 minus 48, right?
Yeah.
84 minus 48 into 1, right?
Yeah.
And use that here and write it as 12 is equal to 48 minus 36 is 84 minus 48 into 1, right?
Yeah.
So you will get 2 times 48 minus 84 is equal to 12, right?
Yeah.
So x is equal to 2 and y is equal to minus 1, right?
Yeah.
So basically what is happening is when you apply the division method to find GCD, you are obviously doing a series of division steps like this, right?
Yeah.
And in those steps, eventually the last non-zero remainder is your GCD, right?
Yeah.
So this is your GCD. So obviously that last non-zero remainder you can write in terms of the other terms of that sequence, right?
Oh yeah.
You will be able to write 12 as terms of 48 and 36, and then you can use 36 and write it as 84 and 48, right?
Yeah.
So eventually you can work your way up to that chain where finally you will write it in terms of the original two numbers.
Yeah.
Correct?
So this means uh the the combination of x and y always exists.
Correct, correct. Because there might be situations where it might be more than two steps. Right now, this was an easy case because there are only three lines, right?
Yeah.
You might have a situation where, for example, if I do GCD of 75 and 144, for example, right?
Yeah.
There might be more steps. Okay, this will also have very few steps, but uh, this will be GCD of 75 and uh, 70, 69, right?
Yeah.
69, and then it will be GCD of 69 and 6. Then it will be GCD of 6 and 3, and then it will be 3, right?
Yeah.
So still this has only 4 steps, but obviously you can write 3 in terms of now 75 and 144, right?
Yeah.
Because you will start from here and slowly remove 69 and then remove the 75.
Like 69 is
Correct,
times something plus 3. Then
correct.
75 is like
Huh.
69 something.
You understood what I'm saying, no?
Oh yeah.
So like this, you will write, keep writing, and then eventually you will get it. So 75 is 69 into 1 plus 6, and then you will write 6 is 3 into 2 plus 0, right? Oh
Yeah.
no, 69 and 6 we have to do.
Six.
69 is equal to 6 into 11 plus 3,
Yeah.
right? And then 3 is basically 69 minus 6 into 11, right?
Yeah.
And 6 is 75 minus 69.
Yeah.
So you can go back and write it in terms of 75 and 144 eventually, right?
Yeah.
So the principle is just that any GCDG can be written as x times a plus y times b, where a and b are the two numbers and x and y are two integers, right?
Yeah.
Now, there is a special case of this, which is called Bizot's identity, which is saying that if GCD of a and b is equal to 1, then obviously there are two numbers, there are two x's and y's such that ax plus by will be equal to 1, no?
Yeah.
X and y are integers, right?
Yeah.
So just like it's basically saying that this is a special case when GCD is 1.
Yeah. But like there's no such steps as the previous one. So like how do we
No,
prove?
there are steps. Thereby will there be no steps? There are steps, no? Like how will you find out that GCD of two numbers is 1? You will do
Oh, so like I still do the
same
division
thing. You will do
and then
b into q plus r1, then you will do a is equal to uh, r1 into q2 plus r2, right?
yeah.
You will keep doing it. Eventually you will realize that
Oh
last remainder is 1, right?
yeah.
Last non-zero remainder is 1.
Yeah.
And then you will keep doing backward steps and write it in terms of b and a.
Oh
You understand?
yeah.
For example, like you can take an example 28 and 13. Let's see, 28 and 13 don't have a common factor, right? 13 is a prime and 28 is okay, yeah, right?
Yeah.
So GCD of 28 and 13. How will you do that? You will say it is equal to GCD of 13 and 2, right?
Yeah,
That is equal to GCD of 2 and 1, right?
with 1.
Right? Oh, it is 1. Yeah, correct. So
Yeah.
you will write steps like this: 28 is equal to 13 into 2 plus 2. And
Oh,
then you
then
will write 13
13
is equal to 6
to
into
5.
2 plus 1. And then you say 2 is equal to 1 into 2 plus 0, right?
Yeah,
So you'll write 1 as 13 minus 6 into 2, right?
yeah,
And you will write 2 as 28 minus 13 into 2, right?
yeah,
And replace this 2 here, right?
yeah.
You will say 1 is equal to 13 minus 6 into 2 is 28 minus 2 into 13, right? So this is 13 minus 6 into 28 plus 12 into 13, right?
Yeah.
So it is 13 into 13 minus 6 into 28, right?
Oh, yeah.
And that is equal to 1. You can check 169 minus 168, right?
Yeah.
So you are able to get the x and the y such that 28 and 13 GCD has become 1, right?
Oh, yeah.
So that is your properties of GCD, and this identity that ax plus by is 1 will become very useful as we will discuss in some problems in the next class. Okay.
Okay.
Uh, so what I want you to do is just go through your text. Also, like if you have any PDFs of or any online copies of your textbooks and all, if you can share them with me on mail, I will get a better sense of what you have learned and all. Like, do you
My
have any online versions of your books or anything?
no, I
Okay.
don't even have a book. I mean, I just walk through random things.
Okay. So in your school and all, you will not have books and all, standard books.
I mean, like, but my school doesn't teach the Olympia thing. They just teach the
Okay.
very normal.
Okay. 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 So far you have been studying for Olympiads on your own without books and all.
I have some books, but like I don't use them. I mean,
Okay.
systematically. I just like when I face a question that I don't know the concept, then I refer to the book.
Okay. Okay. Fine. I just wanted to see what kind of books you guys have. Like, I am not aware of the books that Singapore students are using. So, anyway, it's fine.
No, we
Uh,
also don't have our own books, so I either use the books from China or use the books from the US.
do you have any Chinese books that are in English or something?
I think they have the English translation one. I'm not sure, but the Chinese book is not very good. I think the better one is the US one I
Okay.
bought.
Okay. Okay. So you have bought some US books.
Yeah.
Okay. These are AOPS books, yeah?
Uh, I think it's no,
Not
it's
AOPS. Okay.
no. Because someone recommended me. I
Uh,
can share with you later.
okay, fine. Anyway, I was just curious about the Chinese books that you guys have because from what I know, the maths books and maths levels in China are pretty high. So, and they do very well in the Olympiads and all, right?
Yeah.
So, if if you have any books that you have and which are English translation, then feel free to share it with me. I just want to take a look.
Okay.
But you don't have too many, it seems, right?
I think I have some.
Okay, okay. If they are in English, because I will not understand Chinese.
Okay,
Okay.
I know, but like I don't think I have the online one because
Okay.
the PDF version always they charge very high and
Yeah, yeah, yeah. Yeah, if you have anything that is not costly, or if you have it, then you can share it. Otherwise, it's fine. I just wanted to take a look.
okay, but
Uh,
I only have the physical one.
okay, okay. Then it's fine. Then you don't need to share that. Also, um, you learn through Chinese books or English books,
Right now it's English.
but you can read Chinese.
Oh yeah, I think I'm bilingual.
Okay, fine, fine, fine. Great. I'll see you on 5th then. Okay.
Okay, so like
Hmm.
do I have any homework?
We will have homework in the future, but right now we're just starting out. So, uh,
Understand everything.
Yeah, just read it a little bit, and if you have books for number theory or something relevant, I will find some resources from which we can do homework, but not today. Today we don't have homework.
Okay.
We'll have some homework from the next class onwards.
Okay.
Okay. uh, Fifth is the next class, and after that it will be on Saturday and Sunday. Okay.
Okay.
Okay, I'll see you then.
Okay.
Bye.